Welcome to this deep dive brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today we are taking a detailed exploration into a fundamental idea from Unit 10, wave optics, the coherent and incoherent addition of waves. We're here to unpack this complex-sounding concept and turn it into something crystal clear for your examinations.
I'm ready. I think this is a topic where many of us get confused between the formulas and the actual physics.
Let's start with a simple everyday puzzle then, something to get us thinking. Imagine you have two identical 100-watt light bulbs. If you turn them both on and place them side by side, what do you expect the total brightness in the room to be?
Well, I would say it just doubles. 200-watt bulbs should give 200 watts of light, right? Of a brighter room overall.
That's a perfectly logical expectation, and it's exactly what the geometric array model of light predicts. Intensities just add up. But here is the surprising thing. If you could somehow manage to overlap two special identical light waves, you'd find the brightness is not uniformly 200 watts.
Oh, wait. When you say special, you mean perfectly synchronized? Like they can interfere?
Precisely. Not only can they interfere, but there will be regions where the light intensity is actually 4 times the original. So 400 watts of localized brightness. And here's the real head-scratcher. There will be other regions right next to them where the intensity drops completely to zero.
Pockets of total darkness. Created by adding light. That seems impossible. How can two light waves just cancel each other out?
And that's the moment we realize we have to stop thinking of light as just brightness. We have to see it as a wave. And for that, we need to understand this idea of coherence.
So the whole thing depends on whether the waves are, in step with each other or not.
Absolutely. So let's define the core idea, the distinction between coherent and incoherent. When light is coherent, it means two things are fixed. One, they have the same frequency. And two, and this is the crucial part, they maintain a constant phase relationship over time.
And incoherent is the opposite, where the timing is completely random.
Exactly. For incoherent light, which is what you get from a regular bulb or the sun, the phase difference between waves is completely random. And it's changing incredibly fast.
How fast are we talking about?
We're talking on a scale of nanoseconds or even less, faster than any detector, and certainly our eyes can follow.
Okay, that's incredibly fast. So if it's changing that quickly, how does it affect what we see?
Great question. Let's use an analogy. The marching band model. Imagine 2 rows of drummers. If they're perfectly in sync, they're coherent. Their bass drums hit in perfect unison.
The sound would be really loud and clear. Constructive interference.
Exactly. A coordinated, loud beat. Now, what if the drummers are all hitting their drums randomly, completely out of step? They're incoherent.
The sound would still be there, but it would be messy, right? Just a constant noise.
A constant, uniform, medium loud noise. That's the key. Our ears can't pick out any pattern because the peaks and troughs of the sound waves are flickering randomly and averaging out.
So the synchronized band is coherent, creating a stable, loud, soft pattern. The random band is incoherent, creating a uniform average sound.
Precisely. And this is why lasers are so important in technology. They are highly coherent. That constant phase relationship is what allows them to be focused so tightly.
And ordinary bulbs are like those random drummers because each atom is emitting light on its own schedule.
Perfect mental image. Or think of it this way. Picture a calm lake. If you drop 2 pebbles in at the same time, synchronously, that's coherent.
You'd see a clear, stable pattern of ripples, high waves and low waves.
A stable interference pattern.
Yep.
Exactly. Now, if you just randomly throw a handful of pebbles in, that's the incoherent case.
The surface would just be choppy and agitated everywhere, no clear pattern.
Just uniform, chaotic agitation. The constructive and destructive points are flashing in and out of existence so fast they average out. That uniformity is the signature of incoherent addition. Now, let's connect this to the mathematics. We need to see how NSERT formally defines this, especially for light waves.
Okay, so what's the formula for the resultant intensity when 2 coherent waves overlap?
I'll ask you to read that for us. What does it say for 2 waves, each of intensity I0, meeting with a phase difference of phi?
Okay. The intensity at that point will be I equals 4 I0 cos squared of phi by 2, where phi is the phase difference and I0 is proportional to E0 squared.
Thank you. That formula, I equals 4 I0 cos squared phi by 2, is the heart of coherent addition. That cosquared term tells you everything. It shows the intensity is variable. It depends completely on phi.
I have a question here. If we add 2 lights of intensity I0, why is the maximum 4 I0? I would expect 2 I0.
That is a fantastic question. It's the most important conceptual leap. Remember, waves add amplitudes first, not intensities. So if two waves with amplitude k0 interfere constructively when phi is 0,
Their amplitudes just add up. So E0 plus E0 gives 2 E0.
exactly, and since intensity is proportional to the square of the amplitude.
Oh, I see. The new intensity is proportional to 2 E0 squared, which is 4 E0 squared.
And since I0 is proportional to E0 squared, the maximum intensity becomes 4 I0. That's the peak of the pattern.
That makes so much sense now. It's because we square the added amplitude.
Right. Now for step 2, the minimum. What if the phase difference, phi, is pi, or 180 degrees? Destructive interference.
Then phi by 2 is pi by 2. Cos of pi by 2 is 0, so the whole thing becomes 0.
0. That's the darkness we talked about. Light plus light equals no light.
So coherent addition gives this whole range from 0 all the way up to 4 I naught.
A stable, visible pattern, yes. Now, step 3. Let's apply this to the incoherent case. If the sources are incoherent, that phase difference, phi, is changing randomly and super fast. So we can't look at it at one instant. We have to take the time average.
And the average value of a cos squared function over a full cycle is always 1/2, isn't it?
Correct. So the time average of that rapidly changing cos squared phi by 2 term is simply 12. Now, step 4. We substitute that average value back into our formula. What do we get?
We get I equals 4 I naught times 1/2, which is just 2 I naught.
Which is I0 plus I0. So for the incoherent case, the intensities just add. It all connects beautifully.
Wow. So the simple addition we see every day is just the time average result of the more complex wave formula.
Hope everything's clear so far.
Yeah.
This deep dive is from ProfSam.com. That is ProfSam.com. Okay, let's do a quick worked example because this is where the confusion can still linger. Suppose we have two coherent waves, each with intensity I0. They overlap at a point where the constant phase difference is exactly pi by 2, or 90 degrees.
Okay, so since it's coherent and constant, we use the full formula. I equals 4 I naught cos squared phi by 2.
Perfect. So phi is pi by 2. What's cos squared of pi by 2 by 2?
It's cos squared of pi by 4. Cos of pi by 4 is 1 over root 2, so squaring that gives 12.
Right. So the resultant intensity is 4 I0 multiplied by 12.
Which is 2 I naught?
Exactly. But hold on, here is the trap. If these two waves were incoherent, their resulting intensity would also be 2 I0.
So how are they different? The result is the same.
The crucial difference is uniformity. For the incoherent sources, the brightness is 2 I0 everywhere. It's a flat, uniform light. But for the coherent case, that 2 I0 result is just the intensity at one specific point in the pattern. If you move a little bit, the intensity will go up towards 4 I0 or down towards 0.
I see. So for coherent, 2 I naught is just one value in a changing pattern. For incoherent, 2 I naught is the only value everywhere.
You've got it. And understanding that distinction is the key that unlocks all of wave optics. It's the foundation for understanding Young's double-slit experiment and diffraction. Now let's tackle two silent killers. Common misconceptions that cost students marks.
Okay, what's the first one?
First killer. Students assume that because of energy conservation, if two light sources overlap, the region where they overlap must be the brightest.
Which sounds reasonable, but we just said they can cancel out and become dark. So where did the energy go? Is it destroyed?
No, and that's the brilliant part. The energy is not destroyed, it's redistributed. The energy that vanishes from the dark fringe is the exact same energy that gets added to the bright fringe to make it 4 I0 instead of 2 I0.
So the energy is just moved around to create the pattern. It's conserved over the whole area.
That's the correct idea.
Yeah.
Coherence enables energy redistribution. The second killer. Students confuse brightness with coherence. They think a very bright light bulb must be coherent.
I can see why they'd think that. Brighter seems more organized, more powerful.
But it's a trap. Brightness is just high total power. Coherence is about organization. Think of our drummers. A huge roaring crowd of random drummers is very loud. That's high brightness, but totally incoherent.
And a laser pointer is not very bright, but it's highly organized, highly coherent.
Precisely. So the correct idea to remember is that coherence is a property of organization, not power. Brightness is not equal to coherence.
Got it. Brightness is not equal to coherence.
All right, let's lock this down with some memory anchors.
Okay, I'm ready.
First, remember the acronym COIN.
COIN. What does that stand for?
CO stands for coherent waves, which result in interference, a stable pattern. IN stands for incoherent waves, which result in no pattern.
CO for coherent interference, IN for incoherent, no pattern. That's really helpful.
And a phrase to remember. Coherent equals constant dance steps. Incoherent equals random stomping. Order creates patterns. Finally, a physical gesture. For coherent, imagine two people doing a synchronized dance. Their hands move together, apart, together, apart. You see a clear pattern.
And for incoherent, just imagine them stomping randomly. No pattern, just chaos.
Exactly. Organized pattern versus uniform chaos. That's the difference. So, to summarize this entire deep dive, let's boil it down to 3 essential exam-safe points.
Okay, point number 1.
First, the definition. Coherent waves have a constant phase difference. Incoherent waves have a random, rapidly changing phase difference.
Point 2.
Second, the result of coherence. Coherent superposition gives you a variable intensity pattern, a redistribution of energy ranging from 0 all the way to 4I naught.
And the final point for the incoherent case.
Third, the result of incoherence. Incoherent superposition gives you a uniform brightness, where intensities simply add up to the average value, which is I1 plus I2, or 2I naught.
That makes everything so much clearer. Pattern versus uniform sum.
To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is Prof Sam, right?
Yes, ProfSam.com. Keep exploring the wave nature of light and remember the power of coherence. Goodbye for now.